cardinality of sets. The cardinality definition. The sets A and B have the same cardinality if and only if there is a one-to-one correspondence, highlight that in red, from A to B. When A and B have the same cardinality, we write the cardinality of A is equal to the cardinality of B. Cardinality is a way of counting the size of sets. For infinite sets, it provides a way to do relative measure of the size of two sets. Next, we'll look at cardinality size comparison. We'll do the less than definition for cardinality. If there is a one-to-one function from A to B, the cardinality of A is less than or equal to the cardinality of B, and we write the cardinality of A is less than or equal to cardinality of B. When the cardinality of A is less than or equal to the cardinality of B, and A and B have different cardinality, we say that the cardinality of A is less than the cardinality of B. And this can be easily demonstrated using a cardinality mapping like we did a few sections ago. Next, we'll look at countable sets. We split infinite sets into two groups, those with the same cardinality as the set of natural numbers and those with a different cardinality. The countable sets definition. A set that is either finite or has the same cardinality as the set of positive integers is called countable. A set that is not countable is called uncountable. When a finite set S is countable, we denote the cardinality of S by Aleph null. That is where Aleph is the first letter of the Hebrew alphabet, which is that there. We write the cardinality of S is equal to Aleph null and say that S has the cardinality Aleph null. Next, let's look at an example. Show that the set of positive odd integers is a countable set. In order to do this, we must show one-to-one correspondence to the set Z+. So we have our function is equal to 2n minus 1. That's our definition of odd. And we must show, let's do first the one-to-one or the one-to-one part. And we'll say, suppose that we have 2n minus 1 is equal to 2m minus 1. And if we solve for that, then we're left with n is equal to m. Since that is true, therefore this is one-to-one, going back to the definition for one-to-one. Next, you have to show that it's onto. Suppose t is an odd integer that is an odd positive integer. Then t is 1 less than even positive integer 2k, where k is a natural number. And we have to roll onto a new page here. We'll say Therefore, t is equal to 2k minus 1, which proves that this is onto. Since it's 1-to-1 and it's onto, therefore this is a 1-to-1 correspondence to z plus. Therefore, this is countable. An infinite set is countable if and only if it is possible to list the elements of the set in a sequence indexed by positive integers. The reason for this is that a 1-to-1 correspondence f from the set of positive integers to set S can be expressed in terms of a sequence a1, a2, ... an ... where element a1 is equal to f of 1, element a2 is equal to f of 2, comma ... comma an is equal to f of n, comma ... This way you have a sequence, kind of a graphical way of seeing our express 1-to-1 correspondence, because we have every element is tied to that indexing number.